Okay. So what we are doing today is going to be another kind of wave, but the good thing is it's there's only some aspects of it. All right. And the thing that we are about to talk is about light, which is an electromagnetic wave. So when the word you have when you are talking about the electro and magnetics, so it means you have to deal with electricity and magnetism, which that will be the third module of this course. So that means what we are about to do right here, we're going to pretty much abandon the sinusoidal description of the waves, just sort of like a pocket there. We don't want it anymore. So what we want right now, we're going to turn our attention to just the part of that light, which it's pretty much included in, well, even though it's on the topic say optics, but we are only talk about just only half of the optics, which means we're going to use just only geometry. So this part actually, that is the word, you can put like adjective in front saying that what we are about to do is a geometric optics. So that means is the property of light that we can take care of. We can do the analysis. We can understand its behavior using purely just geometry. Isn't that cool? All right. So it's like kind of fun. Let's bring back um, like middle school mathematics. So there will be no more calculus. This, I'm pretty sure there's no calculus whatsoever. So I think that's a good thing. All right. And
okay,
the algebra, it's kind of light. So mainly it's going to be geometry. So it's going to be a lot of fun. All right. So the main two properties of light, which is the same thing as of waves, that we are going to talk about is the reflection and refraction. Okay. However, we now going to focus on light. So this means there are some things that you can pretty much observe by eyes. That's what we are about to do. All right. So what we did before with the sound, so the observation was made by hearing. Now we're going to make the observation by looking at it. And this is what sort of like an introduction to this topic. Sometimes you can see things like here going like upside down, all this stuff. So there is some weird behavior of the light that going through this lens, and we are going to learn how things go. Okay. All right. What is looking? I don't know. I just got this figure from the web and it looks cool. So I don't know. All right. Anyway, but it's supposed to be like some magnifying glass or something. All right. So, and we're going to learn two properties, which is very important. The name is the total internal reflection. This is so cool. All right. And we're going to end this topics with the image formations. And once we learn this thing, I think that close the chapter of about waves, light, sounds, and everything. Okay. And then we can pretty much come up with the date and time that we are going to take the second exam. Isn't that quick? All right. Sounds good. I need this one to look at my investment. All right. So yeah, I'm into it. This is going crazy now. Too much information going on in this world. I cannot take it. I just sort of like host a Nobel Prize in physics talk yesterday. So there was so many things going on in this, like climate change, global warming, the cryptocurrency. What else? Like electric car. Oh, I don't know. It's crazy stuff. Okay. Even worse than Dogecoin. All right. So many things to learn. All right. So let's get this thing going, guys. All right. And then we can talk about that cryptocurrency like after the class. Okay. All right. So first of all, the reason that we can use just geometry to understand things here, because we only care about the traveling direction of light or of wave, if you would like to expand it to what any kind of waves. And the easiest way to sort of like designate or try to like tell the direction of wave is simply by using arrows. That's it. That's how simple it is. So you just draw a line and give it a arrow for the direction of propagation, and that's it, you're done. All right. But the bad thing about this one is when you have an arrow, then the light, everyone knows, going in a straight line for sure. Okay. So when you have a straight line motion, like, I mean, the easiest way to think at this point is just laser beam, for example. So you can imagine that this is the direction of the laser beam that you just pointed in, okay, in this direction. So by hopefully, by hoping that the beam is just keep going, it's going to be always going in straight line. However, once it hits some obstacle, maybe like, for example, there's some opening here. Think of it like you have like a mini tiny hole here that the light has to go through. After that, I think everyone sort of like know that the light seems to spread out. Okay. So when you have a spreading out of light, then the rays that arrows seems to be like not a very useful tools to tell the propagation of light beam as like a collective properties. I don't know you guys get a sense of this or not. So the idea that we are trying to get to for this particular topic is we would like to discuss about the light when it's still going in a straight line. There's no like dispersion. You still don't want things to sort of like spreading out. So that means you would like to scope yourself and talk about the light when it's still sort of like easy to explain this using just the rays. That's the key. Once you contain yourself within just this sort of like, you know, requirements or whatever the confinements and things like that. So you look at this one. So you might want to send a light through like a lens or whatever, and then the light can just travel. And then it might hit some interface. So that's okay. That's no big deal. But after hitting that interface, it's go in a different direction, but it's still in a straight line. So this is good. So the rays seem to be very useful here. For example, you might want to consider another directions. You're like, okay, that's a light traveling, hit the lens. And then it's sort of like, okay, change the direction a little bit, but it's still going on in a straight line there. Yeah, the ray is still useful here. Okay, or the other one is just like hit the lens and it doesn't do anything, for example. All right, so if these are the cases, then this is under geometric optics. So that means we're going to use just purely geometry to analyze its behavior. All right, so you got the scope of what we are trying to do here. Okay, light is wave and God is Dogecoin. Come on, you guys, you make me crazy at this point. Okay, so this, by contrast to this one, this is the one that we exclude from our scope of this course. The property of light that actually hit the obstacle or opening and then it's spreading out like this. This is called diffraction. So light can disperse out through an opening. This is called diffraction. And by having this spreading out thing, the ray seems to be like a not very convenient tools to use. So this, you have to go back and use sort of like sine and cosine and the waves description and other stuff. So this is, they call it like a physical optics, this portion right here. Okay. So we are not doing this kind of thing. Don't worry about it. All right. So we still assume that everything is just going in a straight line. You can change, you can, you know, change the direction a little bit. That is okay. All right. But all in all, everything can be described using rays, just like an arrow. Okay. So, and the common sense of the ray is, of course, because you only tells the direction of the propagation, the actual fluctuation of the wave, it turns out to be perpendicular to that. So that means if you look perpendicular to the direction of the ray, that will be the actual fluctuation up and down. However, because light is an electromagnetic wave, so you are not having like a particle, like water particle or string particle oscillating up and down. Things that are actually oscillating in light turns out to be electric and magnetic fields. And just wait for it. We are going to learn that electric fields, magnetic fields after this module. Okay, it's going to be a lot of fun and a lot of calculus. So this one is like, all right, guys, cool down. This is going to be the last time that you see something that's non-calculus. And after this, it's going to be like crazy because I'm going to show you the vector calculus after this. All right. Not only just like a regular calculus, it's like a special kind. All right. It's just with no extra charge, of course. Okay. All right. So let's look at the first law right here. It's a simple law. It's called law of reflection. Things just get reflected at an interface. That's it. That's how simple it is. So let's look at this one. If you can represent a light that traveling toward an interface, and you call it an is incidencing on an interface. So you call this an incident ray coming in. Okay. And the law of reflection say if there is a wave reflected off that interface, then you're going to get the condition of the angle of the incident ray and the angle of the reflected ray has to be the same. That's it. That is the simple law right here. Okay. However, the only things that we are going to use over and over again is when you mention about the angle, that angle need to be measured with respect to the normal line right here. So that means every time you have a surface or interface, okay, you draw a normal line perpendicular to that interface. Okay. So we love normal line. We're going to use a lot of this every time we talk about a surface. So that means from now on, every time that you have a piece of paper, okay, so it's a good practice that you draw a line that actually perpendicular to that. Okay. The reason for this is because you can take care of every surface. For example, if you have a curved surface, okay, and if you don't want to use something that's normal to the surface, for example, what some of you like, Ajahn, why do we have to go through trouble defining a normal directions? Why don't you just use this surface right here on the floor like that? And let me draw like a black line. The bad thing about this one is when you have a curved surface, you can see that these lines will pretty much like try to intersect themselves like a lot. And the visualization of this or the way that you explain mathematics out of this is going to go like a little bit like dirty. Okay. So if you sort of like, okay, I don't want to deal with that actual surface. Let's define a normal direction to that, normal direction to that, normal direction to that. It seems like it can take care of the curved surface better in general. Well, the way I say is just actually, I don't really know. I don't really know why, but it seems like it's just for convenience sake, pretty much. It's more convenient when you refer to a line that actually perpendicular to the surface. All right. If you want to use the line that actually parallel to the surface, it's kind of like it's going to get difficult from time to time. All right. You will see that more and more in the third module. Okay. So that's a question comes in. Do light lose energy when it is reflected? Yes. Yes. We can say that for sure. However, once again, we set up everything in like an ideal situation. So we assumed at first that we ignore that option. So we say we assume that everything is nice and cool. There's no absorption of the energy, nothing. So it's 100% reflection in this case, on and on. All right. So we only look at the aspect of the property of waves at this point that has no extra conditions on energy and all this stuff. All right. We are not sort of like, we not take energy losing into account or any heat generated during this interaction with the surface, on and on. So we still ignore that for now. All right. Otherwise, then things would get too complicated. Okay. So the law of the reflection is easy. Okay. However, for the things around you that you can pretty much observe this reflection in action is you can compare between two type of surface. If you have like a smooth, glossy surface, that means that surface has a very nice directions of, I mean, there's no sort of like ridge, there's no like, you know, crazy bump and anything. So the ray that hits this surface will reflect in exactly the same direction. This, we call it a specular reflection. Okay. So the good thing about having the reflected ray going in the same directions means whatever the information of the light that comes in, you can still preserve that on the way out. So when you have something preserved on the way out, that's sort of like appear to you as a reflection. So that's why every time you look at something that is that has a like glossy finish on a surface, you can look see your reflection a little bit out of that. Okay, so that is the property of a glossy finish on the surface. On the other hand, if you have a very rough surfaces, everything just like go crazy like this, light still follow this law of reflection. However, because the surface looks really bad, so the reflected ray going all over the place. So in that case, you lose the information of the incoming information in the light. So you won't see any reflection anymore. So you have a diffused reflection in that case. Okay, so that means if, like, for example, you look at your roof, for example, or maybe your wall that doesn't look glossy, it's just you don't see your own reflection, that means your surface is rough, something like that. Okay, so that's somewhere around you that you can pretty much like relate to the law of reflection, but that's nothing much to it. It's a simple law saying that, okay, in is equal to out. The one that is more interesting, and that will be the main stuff that we are going to do in today's lecture, is this. It's a refraction. All right, so it comes hands in hand with reflection. So refract happens when light, or actually any waves, try to go from one medium to another medium. Okay, for example, here, if you shine a laser light from air and you try to shine it under the glass, for example, go through the glass, or maybe water, or it could be like a polymer, plastic, or whatever. So it turns out at the interface where the light hits the interface, the direction of the ray get bent a little bit. It's bent over here. See that? All right. So it doesn't follow the same path, or I mean, same direction anymore. So what you have here is you have an incident ray coming in, making theta 1 angle. So once again, confirm that the angle has to be measured with respect to normal line. Okay, so that's theta 1. Then it turns out the outgoing ray, that we can name it the refracted ray, going out in a different angle over here. So that we name it theta 2 right there. Okay, cool. So it turns out there are that there is a relationship between theta 1 and theta 2. And that relationship is following Snail's law. So Snail is the one who's sort of like found out that this is the relationship between the angle, and here we go. There is a parameter that we need to define. We call it the refractive index, or the index of refraction. That's the N. Okay, and it turns out this is so common that you can even speak of this as N, like N of air, N of glass. Everyone will know if it's under the context of optics. Every time you talk about N of this, N of that, people will understand that N means index of refraction. So it's that common, okay? So the definition of the N, the index of refraction, is simply take the ratio between the speed of light in the vacuum divided by the speed of light in that medium. For example, if you want to know the N of glass, you take the speed of light in vacuum, which is a constant. It's a constant of the universe, actually. Right. So you know that, right? So that is the highest speed attainable to anything in this universe. So that is speed of light in vacuum. And then you divide it by the speed of light in glass, which in general, I mean, it's not in general, it's going to be lower than the speed of light in vacuum. You will learn more about this because light is an electromagnetic wave. It turns out in the vacuum, electromagnetic waves is a combination of electric field and magnetic field. And it turns out it's trying to, they call it the induce. They induce back and forth between each other. So electric field change, generate magnetic field change, generate electric field change, generate magnetic field. So it's the interplay between this change of electric field and magnetic fields that starts that waves. You call it electromagnetic waves. Okay, sounds good?
Okay.
But then in the vacuum, that induction between electric and magnetic fields can happen without any obstacles. They love vacuum. They love like blank space. So that means when light travel in vacuum, that's when it's going to be able to do that induction the best. So that's why it can travel the quickest in the vacuum. But then you want to send the light into, for example, water. Now the water molecules are charged particle. You have electrons, you have protons, you have crazy stuff going on. And those charged particle interact with electric and magnetic fields. So it makes light induce back and forth between electric and magnetic fields a little bit tougher because, you know, molecules in the way. So that's why the traveling speed is getting lower and lower. So it's pretty much like you can see like a first order approximation. The higher the density of the material, it seems like the light will have a harder time getting through. Does that make sense? Because light has to go through so many molecules and atoms and you know, ion, charged particle, whatever, going crazy. So the denser the material, it seems like the speed of light in that material will be even slower. So that's sort of like a rough idea. All right. So that's why, in conclusion, the N has to be larger than 1 in other material than in the vacuum. Does that make sense? Okay. So N, index of refraction or refractive index, has to be larger than 1 and is going to be exactly 1 in vacuum. Okay, so that's what it is. That's the N, check. So after that, the rest is just Snail's law. So you take N, for example, here, it's going to be N of the air, sine theta 1, must be equal to N of the glass, sine of the theta 2. And the key that you will be able to apply this without getting sort of like going confused or like going crazy is, I would like to add this. I don't know, has anyone talked about this or not, but this is my way of saying you apply this equation at a point. So don't try to think of this application as like you try to apply to like a big waves or anything, or like you imagine like there's a light beam that has like cross-sectional areas. Don't think like that yet, because it will go crazy. Just think at the point of reflection. For example, right here, you just look at this point and be done with. That's it. All right. So that's on this point, there is incoming ray and is outgoing ray. And you just apply this equation at this point, and then that's it, done. And if you say, well, Ajahn, but actual light has some sizing, it's not like a mini line over here. Well, that's okay, because if you know what is going on at this point, it's going to look exactly the same at other points. Then you can pretty much imagine that all the rays that comes in will do pretty much the same at other points. So does that help? Okay. So I hope you will see in our examples that every time that I'm doing this, I will always specify which point that I am analyzing, so you won't get confused. Okay. All right. So before we start looking at that, there's one more step that I would like to show you. Instead of writing this equation in this form, which is a product between the N and the sine of the angle, I can do as a ratio. Okay. So if I want to do that, then that means I can just take this, for example, sine theta 1 over sine theta 2. So if I do that, then I just move N1 to the other side. So it's going to be N2 over N1. So no big deal, John. That is fine. But because by the definition of the N itself, the index of refraction is inversely proportional to the speed of the light in that medium. So it's going to be exactly the same as V1 over V2. You guys with me so far? Okay. Okay. But then you just say, well, Ajahn, we know that for any wave, V equal to F lambda. So that means I should be able to write this as a lambda 1 over lambda 2. That is also fine. Or you can say, well, Ajahn, what's missing is you probably can do this as well. So you can probably say it's going to be F1 over F2. Question, why don't I have this ratio in the slide? Okay. It's not okay yet. Okay. Why don't I have the last ratio in this box right here? Why did I stop the relationship at the wavelength, but not the frequency? Very good. Very good. All right. Okay. Very good. Very good. Exactly right. So you have to be sort of like keep in mind at all time that no matter what you do, you're doing physics, right? So the frequency turns out to give you the number of cycle per second, correct? So no matter what this wave is, the light, the water, the string, or whatever. Think about it. If I have a wave that sort of go in complete one cycle every 1 second, so it means I have like 1 hertz waves. So this means every 1 second, wave has to wiggle up and down complete 1 cycle. And this truth, this fact cannot disappear. So no matter where this one go, you must get one wave, one complete cycle in 1 second. So even though you change the medium, you get into the glass still need to have exact one oscillation per second. Does that make sense to you?
Okay.
So that's keep this out of this comparison. So that means what we are looking at right now is because of the change of the velocity in this medium, what's changed in that medium turns out to be the wavelength in that medium that gets changed, not the frequency. Okay, sounds cool. All right, so that keep that in mind because it's an actual, you know, you, for example, wave in a string, then your hands has to move up and down and up back to the original position. That fact cannot be changed. So it doesn't mean by changing the medium, you get like 2 cycles per second. So you have extra cycle, or you get half cycle per second. So you lose another half somewhere in between. That cannot be done. That cannot be happened. All right, cool. All right. And all right, just to take you a little bit further, guys, the reason that something needs to be fixed, I mean, in waves, allow you to, this is, I don't know, this is going to be crazy analogy or not. It's not analogy, actually, it's the example. When you look at the lights, for example, you will say, hey guys, look at the yellow lights. Everyone will understand what the yellow means, right? Right? Yellow means yellow. Okay. That because your vision, which is like you have a rod cells and cone cell in your receptor, in your retina, and all the stuff, reacting to the frequency of light. Even though the wavelength, the speed of light in your eyeball and the whatever in your liquid in your eyes or the stuff will change already, but the frequency of light won't change. And that's when you interact with your rod cells and cone cells. And then your brain can interpret that color correctly. All right. So that's why something needs to be exact or need to be constant for that particular kind of waves. All right. So I hope this gives you like a grand conclusion of every time you generate a wave, the frequency need to be constant throughout. It cannot be changed. It's already done. I mean, you have a source of the disturbance and you disturb it with exact frequency. The wave that propagating out has to have that same frequency. It cannot be changed. Okay. All right. So I hope I already talked too much, I guess. All right. So once again, n is always greater than 1. All right. So it's exactly 1 in vacuum. Okay. This table gives you a rough, I mean, not a rough, actually, some examples of the n in some substances. So a vacuum is 1. However, because in the air, the gas in the air is kind of like, it's pretty light. It doesn't have a lot of effect on the speed of light. So you can pretty much assume that the n of air is pretty much 1. That's fine. Water is about 1.33. What else are we sort of like familiar with? Quartz, glass, 1.5. So this is like glass windows and the stuff. Salt, 1.5. And this is interesting. Diamond. So everyone know diamond is pretty dense. It's like, you know, one of the highest density material in the world, natural material. So that's go along really well with our understanding. When you have like a super dense material, light have a harder time try to go through it. Right? So that's why n is so big. So that means light travel slowly in diamond. Okay. And from Snail's law, you can draw 2 conclusions right here. So if you have a light trying to go from air to glass, or in general, you want to go from small n to bigger n. So we have 2 values of the n, but now you're going from small to big. From Snail's law, the angle has to go in the opposite sense. So it means angle needs to go from big to small. Does that make sense to you? When you say big to small, means that the refraction of the light will happen in the direction that the refracted ray tend to bend toward the normal. Does that make sense? See, the bending seems to bend towards the normal, which is going to be opposite in the case that you want to go in the different direction. You want to go from, for example, this one big n to a smaller one. So you want to go from big to small n. The angle will go in the opposite direction. You want to go from small angle to a larger one. So in this case, the refracted ray will bend outward, away from the normal. Okay, cool. All right, so this gives you just only the two scenarios. That's it, because it depends on how you change your n. Is that going from small to a bigger one, or you want to go from big to a smaller one? All right. And one conclusion is, if these two material is exactly having the same index of refraction, there will be no refraction. The light will just keep going on. So that's kind of cool. Okay. All right, then. So that's what Snail's law is telling us at this point. So let's take a look at examples. And I think you will see that it's not bad. It's actually very easy to apply. A layer of light strikes a flat block of glass, given the n to be 1.5. The thickness is 2 centimeters at the angle of 30 degrees with normal. So that's very nice. So they already give you everything with respect to normal. So let's draw that one. So I'm just going to draw a normal line there. So the light just get in and hit at 30-degree angle right there. Bam. Okay. Now trace the light beam through the glass and find the angles of incidence and refraction at each surface. All right. The way that you apply this Snail's law is this. So start from here is 30 degree with normal. Okay. Because up here is air. So you can call it in air. Let's take it to be 1. All right. Down here is glass. So this is glass slab over here, a block of glass. And it's given that n is equal to 1.5. And then you come out to the air again, 1. Okay. So you apply your Snail's law at a point. So you have a light hit that point on the block of glass. So I can name this point A. So at A, so you start from any medium that you like. For example, I want to start from the air. So I say n of air, sine of the incident beam, sine 30. Okay, cool. Will be equal to on the way out. I know it's going to be n of glass. So let me put there. All right. And of course, on the way out, there will be some refraction. So the angle of the direction will change a bit. But because right now, I kind of know that you go from 1 to 1.5. You go from air to glass, small to big. The angle will go from big to small. So I think that the refracted ray will bend a little bit toward the normal. You guys with me? Okay. And then I can call this angle to be, oops, sorry. I can call this angle to be theta. Oh, what's going on here? There you go. I can call this angle to be my alpha then, just to change, I mean, sort of have it look different from theta. So I can put sine alpha right there. Okay, and then I can just plug in the value. In air is 1, sine 30 is 1/2, in glass is 1.5. So you should be able to calculate alpha, punching the calculator, and then you're done. Okay?
Okay.
All right. However, at the next interface, you can see that, Bojan, you hitting the bottom interface. So I'm drawing a normal line again. And by geometry, you start seeing that if the upper angle over there is alpha, this is going to be your opposite angle alpha as well. Because you have two dashed lines that are parallel to each other. So you have an opposite angle here. So over there, then you're doing the Snail's law one more time at a point of interface. I can call this point B. Okay. And then you can say at B, you can start from the glass, in glass, sine alpha, because that's going to be your incident angle, alpha. It's going to be, now you come out into the air. So you say in air. And then you trying to just come up with the refracted beam out. But then because you're going from 1.5 to 1 in the index of refraction, I know that the angle will bend away from the normal in this case. All right, so I can just say sine, oops, sorry. Oh, it's too much. Sorry, sine. Whoa, 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 whoa. There you go. Sine. Now I can call this beta if I want. However, when you look at this one, Ajan, wait a second. What you are writing on the left is exactly what you just wrote on the right at point A. So you don't even have to think about anything because that means the beta that we are looking at must be exactly the same as 30-degree angle. Okay, that makes sense? So that means on the way out, it's just going to continue in the original direction that is coming in the top interface right there. Okay, so at the end, what you are getting from this one is it's, you know, you can think of it like it just like there is like I don't think I draw it nicely, but that's what it is. There is some sort of like a translation. It's shift a little bit. When the light going through a slab of material, then it gets shifted. Depends on the thickness of that slab of the material, something like that. All right, but that's what give you, in conclusion, the beta must be 30-degree, just like before. Okay, and that is pretty much the first example of how to apply Snail's law. Key points: apply the law at a point. That will make things a lot easier, I think. I don't even know, is this the right way to teach or not? I haven't heard anybody talk about applying at a point, but that's the word I'm using. Yeah, that's what I think, that's what it means. All right. Okay, that's good. Next, keep going. So I hope it's not, I mean, it's kind of like going, it's easy going pretty much. Yeah, not much. Okay, guys, this is a more challenging one, and I want you to try this. When a rectangular metal tank in the figure is filled to the top with an unknown liquid, whoa, observer O with eyes level with the top of the tank. All right, so you pretty much like, even though this is not totally realistic, but this is, well, doable, close to this scenario. It's just by sort of like glance through the surface of the water. It turns out you can see the bottom of the tank. You can see the bottom corner of the tank. So the corner E appears to you. I mean, you can look at the corner E of the tank. So a ray that refracts toward your eyes at the top surface is shown. So that's the red arrows or the red ray is doing. If the dimensions of the tanks are given, what is the index of refraction of the liquid? You guys try this one. And you don't need this, I guess. All right, guys, try this one. It's not that hard, but it might not be super easy. But I think that's sort of like, you know, wakes you up a little bit in terms of how to use Snail's law. Let's see how it goes. Oh, I just realized that my background is from yesterday talks. Okay, it's kind of very green. It's not very flourish. Okay. All right, guys, try this one. So don't forget, your application of Snail's law has to be done at a point. At a point. So you just have to pick a point where you have refractions going on. All right. And for those of you that still sort of like not sure where, it is this point right here. Right? Because that's the point where the lights try to come out from the water to the air. That's the first step. Pick the point that you want to apply Snail's law. Second, so you have to sort of like, okay, now I'm sure that the interface is going in this direction right there, because the bottom half is water, the upper half is air. Yeah, trigonometry come into play. Yeah, that's geometry. So at that point, you have to draw a normal line. That's a good thing. So you draw a normal line perpendicular to the interface. Cool. All right, now we get pretty much all set up here. Now the rest, trying to apply the Snail's law, you know that bottom here is n of things that you want to find out. So let's call this n. up here is n of the air that we always take to be 1. Okay, so let me name this point A. So you say at A, what happened, guys? You apply Snell's law. You can start from any medium you like. So if I want to start from the bottom, which is has a liquid in there, so I can say it's n of the liquid, sine of what? It has to be sine of the angle that it makes with the normal line. So it must be this one. Let me call this alpha. Okay. So it's going to be n times sine alpha. And then you equate this to the other medium now is in the air. So you put n air in there. And what will be the angle of the incident ray? You say, hi, John, the outgoing ray is just going in the horizontal direction. So the angle must be here. There we go, 90 degree. Got that one?
Okay.
All right. So that means you just put sine of 90 in there. And that's it.
Okay.
From there, then you can pretty much calculate the n. This is the one you want. So you can just say n is, all right, I can substitute n as to be 1. Sine 90 is also 1. So it's going to be 1 over sine alpha. Can you figure this out, Ajahn? That's no big deal because all you need is just the value of the sine alpha. The sine alpha is the opposite over hypotenuse there. You know the length, you know the depth. So this hypotenuse is going to be L squared plus D squared. Okay, so sine alpha will be opposite, which is L, over hypotenuse right there. So let me put it down here. L squared plus D squared. And that's it, guys. N is going to be square root L squared plus D squared over L. And you are done. Okay. And to guarantee that this one seems to be a good it's supposed to be a good one, this number is larger than 1, as expected. Every time that you finish the calculation, and if you end up with smaller than 1 n, something must be wrong. Okay? All right, that's guaranteed. Because n has to be either 1, which is only in the air, in the vacuum, or larger than 1 in other material. So this seems to be checked out really well. Cool. All right, guys, one more, and then we'll take a break. Sounds like a good plan. Is that the pace too slow today? I don't know. It seems like I talked too much. Okay. I thought like I can finish everything like in 1 hour. All right, it doesn't seem to be the case. All right, guys, try this one. Okay, the light beam shown in the figure makes an angle of 20 degrees. Oh, what is that? What about the dimension of the tank? Yeah, you just plug in the number. Yeah, the dimension of the tank. I mean, you plug in the L, plug in the D, and everything else is just a number. Yeah. Okay, now try this one. The light beam shown in the figure makes an angle of 20 degrees with the normal line in the oil. So you have a linseed oil. So it's some kind of oil that you use in painting, I guess. I've seen once or twice in my life. Okay, determine the angles theta and theta prime from the figure. Wow. All right, guys, try this. I'll give you like, this one can be done in like 3 minutes, and then we can take a break at 10:50 exactly. All right, it's gonna be that quick. Okay, first of all, by looking at this, you know right away, you should be able to attack one single point for sure. And it is at this point right here. Because you know the angle at that point to be the incident angle of 20 degrees. The oil index of refraction is already given 1.5. The index of refraction of water is also given in the table. So let me name this point A. So at A, okay, let's start from the incoming. N oil sine 20, you guys with me, is going to be equal to N water sine theta prime. N oil is 1.5, sine 20, just punch the calculator, and then divided by N of water. You looked it up in the table, probably about 1.33, and that will be your sine of the theta prime. So your theta prime can be calculated here, and you're done on this one.
Okay.
All right, not bad. But then once again, the geometry is exactly like what we just saw before. You have two lines that are parallel to each other. and you have a one straight line connecting between them. So the angle of this one on the top is going to be opposite angle to that same angle, 20 degree. So by knowing that, then you have another point to analyze. Let me call this point B. So now you apply Snail's law at B. Again, you can start from the top if you like, n of the air on top, sine of the theta that you want to figure out. And then down there, it's going to be n of oil. And then you have sine of 20 again in the play. Okay. And then what you get over here is sine theta is going to be n of oil is 1.5, sine 20, punch the calculator, divided by n of the air, you take it to be 1, so you can figure out the theta, and you are done.
Okay.
So I think the first half of this lecture just show you how to apply Snail's law, what is the law of reflection, which is simple enough. And then after this, we'll look at a single cool phenomena that's sort of utilize Snail's law, right? So we'll look into that after the break. Sounds cool? All right.
Okay.
All right, take 10, guys. Okay, guys, so what we have for you next is the consequence of that knowing how Snail's law works. Okay, and the phenomena that we are about to talk about here is called total internal reflection. You probably have seen this kind of thing before. Here is an example. When you are under the water, and sometimes when you want to look up back into the air, sometimes or some angle, actually, you won't be able to see anything, but you only see the reflection of the bottom of the pool. I don't know, have you noticed this before? But these figures show clearly that actually at this angle of taking a photo, you can see that the top surface between the water and the air behave like a mirror. So that means the light from the back of the swimmer over here cannot actually going into the air, but it turns out it reflects back to your eyes. I don't know, I write this angle correctly. I mean, you just have to imagine like a perspective a little bit. So it's go like this and it try to get to the air, but it's not, it's sort of like bounce to your the camera or something like that. So this is the idea of light. Instead of doing the refraction, which in general you expect that the light supposed to hit the surface of the water and just go out there and you won't be able to see anything. But it turns out when there is light actually hitting you and your eyes and your brain just interpret that, hey, I can see something there. So that means the light, instead of going out into the air, is just bounce back and hit your eyes. So that's why you can see what is going on the back, but it appears right here. Okay, does that sounds like something that's relatable, I guess? All right, so the reason that this happens can be explained using Snail's law that we just learned. So let's take a look at this scenario over here. All right, so I mean, now we know that if you start the light, in this case, like for example, in the pool, so that's mean you start from something that has a big index of refraction, let me call it like a big N, like water. And up there you have air, which has a smaller n. So that's a small n area of that one. If the light trying to go from a big N to small n, you know that the angle will go from small to big, correct? And we already learned that if the light hits the water or hit the interface, the refracted ray will bend in the direction that's away from the normal. So that means the outgoing ray will have the angle bigger than the incoming ray. Okay. And now if you keep increasing that incident angle, you can see that now you getting the incident angle bigger. Now your refracted ray will get even bigger because it has to bend away from the normal. You keep increasing it again. So what you have here is at point D, now your incident angle is growing bigger. Of course, your outgoing ray will going even bigger, even. See that? Keep going. So that will be one particular angle that once you hit it, it turns out your outgoing ray gives you 90 degree. So what will happen next? So you say, well, Ajahn, what if I keep increasing the incident angle? for example, at point F. So now your incident angle is beyond the angle that give you 90-degree refracted angle. It turns out the light will not get through the other medium anymore. Well, forget about it. There's no condition that I can make anymore. So the rest of the light will not penetrate to the second medium, but it will get reflection. And it's total reflection because everything gets reflected back totally. Okay, sounds good. All right, so this is a consequence of the light trying to get from bigger end to a smaller end. You have a chance of hitting something that we named here, critical angle. So every time that light try to travel from a big end to a smaller end, there is a critical angle between this pair of the medium. Okay, and if the incident angle go beyond this critical angle, you will not get refraction anymore. You will get 100% reflection at the surface. Okay, sounds good. There's a question comes in. Does the critical angle change with frequency of light? It turns out yes, but well, it's actually it has to be everything actually turns out to be a function of frequency or wavelength. But for our purpose right here, we just try to make it simple. So we assume that glass will have the same value of n. Does that make sense to you? All right, actually, this is a very good question, but it seems like an advanced question in the sense that when I say n of glass equal to, let's say 1.5, assuming, we assume that no matter which wavelength of light that you send it in, it will travel with the same speed, but that's not actually the case. Okay, but we don't want to deal with that now because it turns out n of glass can be written as a function of wavelength or frequency for that matter, if you want. Okay, but we prefer wavelength because it changes with the speed. So by having n as a function of lambda, it means different color of light will travel with different speed. And that's the reason why you see like 7 colors or the rainbow colors in like an air in the water droplet or in the prism or whatever, something like that. Okay, sounds like that answer your question. So in reality, n of glass is not a fixed number. It's a function of wavelength. But now, just make things easy. We assume that you can shine the light, the red, the blue, the green, the yellow light, it will travel at the same speed, according to index of refraction of 1.5. Okay, all right, come back here. So that's good. So what we have over here is now we can always be able to calculate critical angle. So this is the angle that sort of like draw the line between you are going to get refraction or not. If the incident angle is larger than critical angle, that's it. You won't get refraction anymore. Everything will get reflected back. Okay, sounds good? All right. So before we start looking at the example, over here, I have some comments on this particular diagram here. If you look carefully, I think this is a very good diagram. So you might be wondering, Ajahn, why at point B, for example, you have a refraction here, which is no problem. But then why this diagram draw a reflection as well? The answer is, it turns out, if you do a detailed calculations of the electromagnetic wave fluctuations, it turns out if you come in with 100%, I mean, let's say 100 units, let's say, right? We don't care about the units at this point, but let's say you have 100 units of light coming in, hitting the interface at point B. It turns out you might get only like maybe 96 units penetrated through the air. And then you might get like 4 or 5 units reflected back no matter what. And it seems like as long as you're not hitting the critical angle or beyond, you always get a little bit of reflection all the time. That happens. That's general for waves. Any waves that trying to go from one medium to the other medium at the interface, some of it will get reflected. This is the reason why when you look at the glass, like a transparent glass, you always see a little bit of your shadow. I mean, it's not shadow, a little bit of your reflection. No matter how you sort of like, you know, you want to wipe with the super wipe. I mean, you're gonna like, you know, clean it up. No matter how clean your glass is, you're going to always see your own reflection, a faint reflection of yourself all the time. Okay. And that's part of it. Every time that you see a little bit of yourself through the transparent glass, and that's because a partial light get reflected back to you. All right. And like 95% go through on and on. All right. So there is no, I would say, super clear glass doesn't exist. There's no glass that is like 100% clear until you see nothing at all. I mean, it's like there's no glass there. That's not possible because the end of glass is different from end of the air. So you always get some reflection back every time that light try to change the medium. Okay, sounds like
Okay.
relatable. All right, just so you know. All right. However, there is some engineering things that they can generate, like a super, like highly efficient glass that reduce the reflection, and then they use that in this laser technology and all this stuff, of course. But you need like you need some factor or some engineering into the place, and then you have to take into account interference effects and all this stuff to minimize the reflection. Okay. All right. So the ray A is impossible. Yeah, the ray A actually is easiest because in this case, the incident angle is 0. So the refracted ray is also 0. So this one is just going straight out, just going penetrated out. But a fraction of it will get reflected back anyway, like 4%, 5% get reflected back. Yeah, all the time. Yeah, so A is possible. There's no big deal. So light just shoot up, straight up. But then there'll be some of it get reflected back. Okay, sounds good? All right, so by talking about this, I think it's a good thing that if I refer back to this one. So in reality, it turns out when light hit the first interface on the top, there'll be like a 5% getting reflected up here. Okay, let me use like a highlight here, just like a faint one. Okay, so there'll be like a little bit of stuff sort of reflect here. And when light hit point B, most of them get penetrated, but a little bit will get reflected up. Seriously. And that light, once is bounced up here, it will refract out. But then part of it will get sort of reflected back again here. And once it hit down here again, part of it will get refracted out, and part of it will get reflected back here again. But it's getting sort of like more faint until it just disappear. Okay, so every time that light or any waves try to change the medium from one to the other, most of them might get refracted, but there will be a partial part of this one gets reflected back all the time. All right, so that's why every time that you have this kind of like a slab with some thickness, there'll be like multiple reflection inside. Okay, and if you combine the interference effects and everything, then you can play cool stuff in here that you can minimize the reflection, or you can minimize the transmission, and then you can create a kind of like different kind of windows that have like a super transparent glass or something like that. All right, that's kind of cool. But all right, we are not trying to get to that. It's going to be too complicated. Is the 5% a slightly different wavelength light? Is a slightly different wavelength light? 5% is actually came from the property of electromagnetic wave fluctuation. So the reason I say approximates, because most of the time we talk about glass, and the glass has the end about 1.5. So eventually you get about like 4 or 5% reflection. Yeah. So it just came from, not because of the wavelength, but it's because of the electromagnetic wave is trying to get from one medium to the other medium. And by the thing that you're probably not going to learn here, like there's a Maxwell equation that you have to meet some requirements, boundary conditions, on. And then eventually from that theory, it confirms that 5% or so will get reflected back to the original medium, something like that. Yeah. Okay, so it seems like textbook try to not overlook this particular fact that every time that there's a medium's change, some of it will get reflected back to the original medium. So that's why they try to draw a diagram in this way. Okay, all right, guys, cool. So how can we figure out the critical angle? Question. The answer is easy, บอกอาจารย์ because the critical angle happens when the refracted ray is 90 degrees. So all you need to do is just set, oh, maybe it's here, just set this outgoing angle to be 90, and that's it. Once you set that to be 90 degrees, whatever angle that you're looking at in the incident beam, that will be your critical angle. And that's how you evaluate the critical angle. That's easy, yeah?
Okay.
Okay, let's take a look at how to apply this kind of thing. But before we get to that, can you guess what is going on in our lives right now that use this kind of thing? Yeah, it's optical fibers. We're using high speed internet and all the stuff. We in depth of, yeah, total internal reflection, guys. That's allow us to have like a broadband data transfer, all this stuff, because optical fiber rely on the internal reflection of light within that fiber. All right, even though this figure looks very fake, because in reality, you're not getting like reflection like this. What we learn over here is, okay, of course, it's the internal reflection, all that stuff, but this is just a diagram to represent what's supposed to be going on based on the internal reflection, right? But in reality, what they do in a real fiber, they're not using a single end core. Okay, right? So in this case, you probably expect from our class, well, you can pick like glass, maybe n equal to 1.5. And we assume that we send in the light and the light will just bounce back and forth like this. But that's not the case. It turns out engineer trying to optimize, or actually even try to maximize the amount of light that can stay inside the fiber. So what they do is, instead of generate a glass, a fiber, which is a fiber itself, it's not like a real glass. It could be a polymer and all the stuff. But instead of having a single value of N on the glass or on the fiber, what they use is they have it's the N that actually changing its value. So that's kind of cool. So it means when you go from the core and go toward the outside of this fiber, the N is changing. So it has a higher N in the middle, and then it's trying to go to a smaller N outside. The good thing about that one is you sort of like have a multiple. Well, when I say multiple, it's sort of like a continuous. Like you have a multiple total internal reflection all the way from the center of the fiber all the way to the rim. So instead of having like just a straight line of light going through and then bounce back and like this, just like what we just studied, by having it's called the graded index like this, it's like there's a multiple total internal reflection, total internal reflection, like, you know, everywhere. So at the end, effectively, it's like light seems to go in the curve like this instead. Does that make sense to you? So you sort of like, you have like total internal reflection on top of each one all the time when you go through another layers. So by having this, you compare this with just like a straight line. So you get more light to stay within the fiber. So by designing the index of refraction has like a changing value from the core to the rim, you enhance the output or throughput, even like, I don't know, 20 something percent or 25% or whatever. All right, so that's the engineering thing that you can do, okay? So there's a question, oh, how is it better than copper wire? Okay, so if you were at the time of the ADSL, the high speed that based on the telephone lines, so the telephone lines just use the copper wire. So when you send the information through the copper wire, that means you still use electric. So you use the electric signal, and that's based on the electrons. The bad thing about electrons is they are charged particle. So when they are charged particle, when they are close by, they will interact with each other. So that means there's so much that you can put in one single copper wire until the density is not, I mean, you cannot push the density as high as some limits because the interaction between electrons themselves. Okay, so, and that limit is pretty low because it's a current flow in that wire that limits your amount of information. But once you move from electrons to light, like what we have in the optical fiber over here, it turns out light is wave. And you learned from interference last week that wave when they meet, they may interfere a little bit, but then they pass each other by without any interactions. So that means you can squeeze a lot of light into a single fiber without having lights interact with each other. Okay, sounds like a good explanation here. All right. So that's why light is way better than electrons in sending high density data. And actually you can pretty much like, you can see the enhancement of this one is like 3 order or 4 order of magnitude, or even actually 6 order of magnitude higher density with respect to the same single amount of material used. All right. So that's where we are. And I think that's where we go. We pretty much in the future, I think we're going to rely more on lights, because copper is I mean, electric is going to get stuck somewhere somehow. And even for those of you that are doing computer science, I think you guys know, but I think we have pushed so far in terms of like, for example, the CPU, the chip and all the stuff that use electricity. There were like a prediction saying that you're going to hit the limit somewhere like back like 10 years ago. But until today, I used to have like Intel Core i7, i9, or Ryzen 9 or Hyper, I don't know, whatever things that's still going on. So instead of having to push the wire into a smaller and smaller, and you're trying to push higher density of data that going in the CPU, they do like a multi-core processing instead. So you pretty much, they get away with parallel computations. So they have like a, 8 core, like 6 threads and all this stuff. So they sort of like find a way out by having something in parallel, or they're doing like a 3-dimensional structure, silicon on chip and all the stuff. But eventually, I would say maybe give it another decade or so, you're going to hit the wall somewhere. Okay. And eventually there will be a bridge that connects between electrons, and eventually it will be optics, and that would be light as a data carrier. So I think maybe, but it takes time, right, for the adoption of the new technology, and you need the infrastructure to be there first. So it takes time, I guess. Yeah, but it will be here somewhere. Light seems to be a higher form, more versatile, and there's still a lot more properties that we can utilize with light than just electrons. So, right. So in your lifetime, you'll see new technologies, and yeah, you're still waiting for metaverse. Come on. I know that's another world there. Yeah, Facebook is just going crazy. All right, so maybe next decade we can study everything in metaverse now. Right? So not forget about work from home. It's just work from metaverse. Yeah. So all right, that'll be like a virtual university. No one has to go there anymore. Just log into the metaverse and then pick your university. Link this optical fiber to my brain. Oh, wow. No kidding, guys. Yeah, eventually there will be some interface to your brain. That's what Elon Musk is trying to do right now. Yes. So there are, what is that, Neuralink or whatever? Yeah, they're trying to do some yeah, it's it's the interface between your brain and something else. It's working. It's going on right now. Yeah. Yeah, you were joking, but no, Elon, not joking. Yeah. There is a project going on right there. Yeah. So, I mean, it's early stage, but it's something is going on there. And if you keep pursuing this sort of like this ends of the technology, light is amazing, actually. There's so many things going on with light, even from relativities, space-time, you do quantum physics, and then you do like encryption and other stuff. For those of you that doing computer science, I think you guys seem to hit this one either soon or, I mean, someday in your life. You cannot avoid it. You're going to have some quantum encryption is coming in. So quantum computer is also sort of like starting to get hype again. And then I think it's in the next decade. I think it's here. Yeah, cannot, I mean, we going crazy now. That's what I'm saying. All right, guys, let's get back to our business over here. All right, guys, take a look at this and then calculate the following. So find the critical angle for the following material surrounded by air. So don't forget, every time that you would like to calculate critical angle, those critical angles must be specified between two material. Like here, we always need two material, right? Like here, a pair of glass and air. Yeah, so it has to be critical angle between what and what all the time, okay? So it doesn't make sense to have like, hey, find me the critical angle of water by not saying that and what. You have to do and. So in this case, it's surrounded by air. So it means they want to know the critical angle between diamond and air. Okay, so what you do is just, okay, John, it's just, okay, if you imagine there's like a surface of the diamond, so that would be an N diamond down here, in air up there. And then, of course, every time that the light tries to escape from the diamond into the air, there is a chance that this will hit 90-degree angle on the way out. And this is the condition that you can figure out the critical angle. All right, so I hope this diagram showing you what is going on right now. So what you have here is you applying the Snail's law at a point of refraction. Yeah, no big deal. So at that point, you can say N diamond sine of the angle that's now is going to be our critical angle is going to be N of the air on the way out is going to be sine 90. So by doing this, you don't have to memorize any formula. You just know that the condition is the refracted ray is making 90-degree with the normal line. So this one goes to 1, and the sine of the critical angle is just in air. You can put 1 into it. In diamond, you can look it up in the table, and it's about, let's say, 2.4 approximately. All right. All right, guys, can you figure out what will be the theta C here? The reason I want you to try is because make sure that when you punch your calculator, you use the correct unit. Because, of course, some of you guys just config your calculator to be in radian, and some of you config your calculator in degree. All right, so make sure that you get the final answer correctly calculated. Okay, all right, and then by doing that, okay, for those of you that have time, figure out that theta C for me here. I'll do it the same for glass. So same thing, same diagram, but it's just replaced end of the diamond with end of glass. So it's going to be end of glass, sine of the theta critical. So let me put like G for the here. So it just distinguish between the part A and part B. So it's just critical angle between diamond and air and critical angle between glass and air. So on the way out is still end of the air. And then you put sine 90, which is 1. Same thing. So sine of the theta critical in case of glass and air is going to be 1 over. In glass, it's about 1.5. So you're going to get theta C in this case to be something. All right. So did you get the angle? I think if I remember correctly, for the diamond, I think it's about 24 or something, a little bit, somewhere around there. And for the glass, it's like 42 maybe, I don't know, but it's somewhere around that area. Okay. So do you feel anything about this one? No, I don't feel anything. I don't want to feel anything at all. I'm just kidding. So does this numbers sort of like tells you something about diamond and glass? What do you think? You get like for the diamond, the critical angle is only 24. And for the glass, it goes up to 42 or so. This is the reason why diamond is sparkling. Yeah, it's shiny because it only takes the light to go only beyond 24. It will not penetrate to the other side anymore. It gets reflection. But for the glass, it has to go up to 42 before you start to see reflection out of it. So this is the reason why the material that has a high index of refraction, like diamond, will have a tendency to showcase the reflection more. And plus, you do the diamond cuts, put that on top of just like a raw diamond. So with that diamond cut thing, yeah, so you can actually enhance that sparklingness and all this stuff. I don't know, is this the right word or not? But that's the thing is because when the light try to get into it, it's so easy for it to get back. Okay, when light hit here, it doesn't want to get out easily. It's trying to get out back here. And this is also the reason why the diamond shape is very specific. if you sort of look at the shape of the diamond around the world, it has pretty much the same shape. So it looks like there is a specific angle of the diamond cut that you need to do. And that particular angle actually came from this factor over here. They try to optimize the way that light enter when it enter the diamond. It's sort of like maximize the return. So make things like, bling bling and shiny, all this stuff. All right. So that's why you won't get any, shininess. I don't know, is that a word or not? But anyway, of course, glass that you use for water, not going to be so shiny. Okay. Yeah, spherical diamond is not going to be that bling bling, but you get more reflection, of course, but it's not going to be, shiny and then give you some splash to your eyes and other stuff. Okay. And if you look back at the table over here, so if you have here sapphire, you can see that it's a little bit better than glass. Of course, it's 1.77. So that's why if you look at like Swarovski's, other stuff, so it has a higher value, of course, than just purely just like a glass material. Okay. And it's not, but of course, it's not as valuable as diamond. Okay? But as you can see, it will give you more bling with respect to glass or water, ice cube, for example. I don't think we're gonna see any, shiny ice cube or anything. That's gonna be tough. All right. Okay, try again, guys. So let's do a couple more of exercises. I think it will be done. I think that's it about this. I hope you see that this is easy enough for today's lecture. It's purely geometry, and we rely on only single equation, Snail's law. It's kind of nice. Okay, in the figure, a ray of light is perpendicular to the face AB of a glass prism, given n. Find the largest value of the angle phi so that the ray is totally reflected at the face AC if the prism is immersed in air. And of course, once you're done with that, let's change it to water. All right, you want to give it a shot? Okay, this is like the kind of question that will show up in the exam, right? Just want to test that, okay, you know how to set things up, how to apply Snail's law at a point, and then you know how to calculate the outcome. Okay, so this is sort of like may trick you a little bit at the first interface AB, because at the AB interface, when you look at this one, the light just hit this interface dead on. It's just like zero incident angle. So with that, then there's nothing happen at this interface. The light just keep going. Okay, so you don't need to worry about anything on the surface AB. Sounds good? All right, even though you might say, oh, Dan, all right, we have a little bit of reflection. All right, just forget about it. All right, we kind of know that, all right, 96%, 95% just, go through. Okay, now the key sort of like event that's going to happen is going to be at this point right there. So first thing first, just draw the normal to that interface. All right, so that will be your normal. So by drawing that, you have to make sure that the angle of incidence that you're gonna put into your calculation has to be this angle right here. Let me call this alpha. Okay, make sure that the angle that you put in your formula has to be the angle that measured with respect to normal line. Yeah. All right, and because we would like to set the conditions that what will happen at the critical angle, because that will be the sort of like the angle that's sort of like draw the line between you're going to get reflection or not. So the way to do that, you just set the, you want to set the outgoing ray to be once again at 90 degrees. You guys with me? All right, because this will be the conditions that you want to check that you will get total internal reflection or not. So, okay, so we'll set that one. And then let's call this point A. So at A, sine, okay, let's start from the prism there. N prism sine alpha, you guys with me? Okay, N1 sine theta 1 equal to, on the way out, in this case is air. So out here is air. So it's going to be in air and then sine 90 degree. Okay, not too bad.
Okay.
All right, and then what you have here is just try to relate to the phi. Sine 90 is definitely 1, so this one is gone. In air is also 1, that is fine. So what you have left to do is just what is the relationship between the alpha and the phi? And then once again, you use geometry. When you look at this one, oh, that is just a similar triangle. If this is phi, this is going to be phi as well. Okay, cool. All right, so now you know the alpha is just 90 minus phi because phi plus alpha is just 90 degree right here. So perfect. So what you can do next is end of the prism is 1.5 and it's going to be sine of 90 minus phi, sorry, minus phi right there. Let's go to 1. And everyone knows sine of 90 minus phi, you can rewrite it as a cosine. So you can write it like cosine phi is 1 over 1.5. And that's it. You figure out what should be defined. It's just inverse cosine of 1 over 1.5. And you are done.
Okay.
Okay. When you say done means this gives you the pretty much the value of the phi that draw the line between you're going to get total internal reflection or you're just going to get refraction into the air. Okay, cool. All right. And for part B, if you want to redo everything again, everything is exactly the same, except now the environment is replaced by water, which is fine. Well done. I can just replace water is supposed to be blue, I guess. So I can just turn this outside portion to be water. It's no big deal. The only thing that you need to change over here is just at A is still end of the prism. Sine is still sine of alpha. Nothing's changed. Outside, instead of air, you turn it into end of water. But you still set the outgoing ray, the refracted ray, to be at angle of 90 degrees, just the same. Okay, so everything works exactly the same, except you replace end of air with end of water, which you can say is about like 1.3 or so. And then you divide by 1.5. And then you should be able to figure out the phi, just like before, and you're done.
Okay.
Okay, not bad. So I would say this is the easiest lecture of all. I think so. I'm pretty sure. In comparison to every other lectures that we have done in the past, I think this is, well, I don't know if you like geometry a little bit. Okay. Okay, last one, guys. Just give one more. Any questions so far? How does this explain one-way glass? What is one-way glass? Let me guess. What is one-way glass? Oh, you mean the glass that's outside people cannot see inside, but the inside people can see only outside, something like that? Is that one-way glass? Okay. Okay. That one-way glass, it turns out they have, it's the enhanced reflection by outside of the glass. It doesn't have outside or inside, doesn't matter. But the glass is like you can think of it like let's say a 50% reflection. Okay, 50% reflection. So that means when you look through the glass from the outside, people will see their own reflection because the light outside is brighter than the inside. So they will see a lot of the reflection back to themselves. But for the people inside, which usually darker because you are in the office, for example, try to look outside, you will still be able to see it because the light from the inside won't get reflection as much. So you can still it seems like you can, can look at things that actually penetrate through the windows. Does that make sense? So the way that you can sort of like, if you have like a one-way glass like this, the way that you want to look inside is you have to get very close and then you sort of block your eyes like this. Yeah, when you do that, then there's no light from the outside interfere with whatever you're seeing, and then you can still see who is inside. Or if you look at this office at night, let's say you turn the light in the office and you stay outside, then you can see what's going on inside more easily. So it's not like a one-way glass or anything. You just get more of the reflection during the daytime from the outside. That's all. So I would say the one-way glass is the partial reflected glass. Maybe they can put like 35%, 50% reflection, like maybe a mercury layer on top and all this stuff. Yeah. Okay. All right. That's a good question though. Yeah. I was wondering the same thing when it was like small and it's like, hey, what's going on with this kind of glass? Okay. All right, guys. Last one. Okay. And then I think that's gonna be done. But I hope this sort of like make you feel very comforting. it's a it's like a you don't need to worry too much about this kind of question in exam. So this will be the upper limit of the question that will show up in the exam. All right. I don't think it will go any harder than this. All right. So everyone try this. In the figure, a light ray enters a glass slab at point A. So it's on top surface there. And at incident angle of 45 degrees. Okay, that's given. And they already gave you the angle that's that's measured with respect to normal. So this is good. And then undergoes total internal reflection at point B. Okay, that's good. The reflection at A is not shown. Okay, that's fine. All right, we know that part of it will get reflected back. What minimum value of the index of refraction of the glass can be inferred from this information? Okay, so now they just reverse the question a little bit. So they just say, hey, the situation gives you the total internal reflection. So what should the end of the glass be? Okay. And what is the minimum? Of course, you can increase the end. You have more chance to get total internal reflection. We sort of know that from the example that we did, the diamond and glass and all that stuff. So that's why they're asking for the minimum value. What would be the minimum value that you will get out of this? Okay, so let's dive into this one. Once again, we apply this 1 point at a time. So let's start from the top interface at A. Okay, so you can say, well, John, that's no problem. We start from the outside in air. It's up here in air. And the incident angle is just theta 1. So sine theta 1. Everyone so far so good? Okay. Equal to, now you enter the glass. So it's going to be in glass. And then let me call this angle alpha. So that is your sine alpha. All right. So now in air is 1, that's fine. Theta 1 is 45 degrees, that is also fine. But now we have two unknowns. We don't know the end of the glass and we don't know the sine of the alpha just yet. So let me sort of like park this one here. So let me write it like root 2 over 2 equal to n sine alpha. Let me name this equation number 1 and assume that the glass has the index of refraction n for now. So you do this at point B. But then because we just want to get things started, what would be your minimum requirements for this total internal reflection to happen? The way that you do that is, once again, draw a normal line first. And because we want just like, starting point that things will start to get total internal reflection, you take the condition of the outgoing ray to be at 90 degrees. You guys with me?
Okay.
Okay. So once you have that, then don't forget the incident angle has to be the angle that's measured with respect to normal. There you go. Let me name this beta. All right. So at B, let's start from the glass. So I would say in glass, sine incident angle beta must be you go out into the air. So it's going to be end of the air, sine 90 degrees. In air is 1, sine 90 is also 1. In glass, we just call it n, sine beta. But then, John, wow, I don't want to introduce new variable into this anymore. You can see from this, beta and alpha are related because if you draw this a right triangle, beta is just 90 minus alpha. So it's just 90 minus alpha is equal to 1. So I can rearrange this one a little bit. So it looks like 1 equal to n sine 90 minus alpha is cosine alpha. So let me name this equation number 2. So now you have 2 equations and 2 unknowns. Now you can solve for anything. So because they would like to figure out the n, So you can solve for, I mean, the easiest way, just take the alpha first, because I can do 1 divided by 2. I would get 10 of the alpha. I just eliminate n out of the picture. Is going to be root 2 over 2. So from here, I know what should be my alpha. And then I just plug in into 1 or 2 equations, and I can back solve for the n. So n is supposed to be something, and you are done.
Okay.
Okay, sounds good. So as you can see, everything just revolve around Snail's law. That's all. All right. But the good thing or the cool thing that just pop out from this is just when you take the refracted ray to be at 90°, you are at the limit that the light does not want to do refraction anymore. If you go beyond that, and that is the critical angle. So if your incidence angle just, just go above your critical angle, then you get 100% reflection. And that is done for today's lesson.
Okay.
Thank you for sticking around. All right. And take care of yourself. And I'll see you guys, well, on Monday. But during this, so Monday, I hope I will get the exercise done, do the grading, everything. I hope. All right. I'm catching up right now. So many things going on. All right, guys. Take care. Bye-bye. I'll see you next week.